general relativity, step by step. Before I start, there's one thing I've got to do that's been driving me nuts over the weekend. I'm going to rewrite this off-axis, off-diagonal term. It's h sine theta sec cubed theta. H sine theta sec cubed theta, and here's h squared sec to the 4th theta. It's been driving me nuts. I think it's a much better way of doing it because you haven't got a tan term. It's just an easier term. You may as well put as much as you can into the form of sec. Right, we've been talking about taking dot products, and what we call v dot w is equal to vi wi with an implicit sum over I. So there's one contravariant index here and one covariant index here, and we're summing over the I, and that's equal to the dot product, which equals a scalar, of course. Now what I'm interested in is v dot with itself equals what? Well, just following the formula, it's sigma vi vi. Vector v has got components vi. Well, what's this? That's no problem because we've got this. But this beast here is a peculiar thing, and I'm going to talk about what it means to take an index from a superscript position to a subscript position. V dot v equals, by definition, vi vj gij with an implicit sum over I and j, which I'm going to try and avoid writing. Well, we've covered that many times in the previous screencast. What I'm going to do now is to bracket it like this, and I've got vi, and you'll notice, well, I could call this anything. This thing in the brackets here, I can call it x, and it's a subscript I. And that equals v dot v. Because this thing here, it doesn't have an upwards index, it doesn't have a downwards index, because it's been summed over this j here. All it's got left is this I here, which is in the downward position. Just call it x. And it's conventional to call it the same symbol v. It's the same symbol with the index moved down. You can tell this is a contravariant. This thing here is a covariant vector. Covariant. So with this thing here, with this definition here, we know that vi equals, by definition, vj gij. So effectively, we've turned vj into an object. Vj's got a superscript index. This character here, this object here, has got a subscript index. So it turned a contravariant vector into a covariant vector. We've not really converted it as such. I mean, it is what it is. What we've done is multiply by the metric tensor. But what we can do is calculate v dot v equals vi vj, where we understand, oops, I meant to write j, that vj equals vi gij. And we call this, which is vi goes to vi gij equals vj. We call this process lowering an index. Okay, so it's a handy way to turn a contravariant index into a covariant index, simply multiplying by the metric tensor and contracting over doesn't matter whether you do it over the first or second index because it's symmetric. Yeah, I'm going to stop there.